series by MIA Specialist Group, IWA MIA Specialist Group. So my name is Sabo Daneshkar, and I'm a vice chair of the MIA Specialist Groups. And on behalf of Elena Torfs, the chair of this group, I'm gonna give you a brief introduction to this specialist group, who is the body behind organizing these webinar series. Yeah. So MIA, so Modeling and Integrated Assessment, is one of the 50 or 52 specialist groups of IWA, and we are one of the most active ones, in fact. And generally, as probably the name suggests, we are dealing with modeling and integrated assessments of water systems in general. So not specifically on one part of the water systems, but we cover and try to connect people from academia, industries, and everybody that is active on modeling and optimization of these kind of systems, from surface water to wastewater, drinking water, whatever that can be related to water systems in generally urban areas. So we have an active IWA Connect Plus page that you can see on the right-hand side of this slide, and also the website of the MIA, which is also quite updated with all the information about the management committee, about the activities that we organize or we do, and you can get a lot of information from there. But just a brief highlight of the main activities that we organize and do at MIA. So we have quite some task groups and working groups within this specialist group, and task groups are usually a group of few people that they join to do a certain task, and you can see the examples of that. Which, for example, the good modeling practice (GMP) is probably one of the most famous one that was done some years ago, let's say, by a group of people from the specialist group at MIA. And we have now the number 2, for example, running currently. And at the end of their time, they usually publish a scientific and technical report as the summary of the whole activities that have been done during the few years of the activity of that task group. Working groups are also a bit similar, with usually a bigger group of people and with an unlimited time. So they're not specifically working on one task, let's say, but they are generally working on a broader domain than task groups, and they also continue a bit in a longer term. And sometimes they also publish an STR, but not necessarily all the time. But for example, the CFD modeling working group was also a working group that they published a scientific and technical report. These reports are generally all published by IWA, and almost all of them are available as open access reports that you can get access to. Then for the conferences, I will say a few words in the next slides, but webinars is also, as you see and you're here, is one of the other, let's say, important activities that we do organize. So we do organize a few webinars, 4 to 6 webinars per year on different topics related to modeling and integrated assessment of water systems. And you are sitting right now in the series about the digital twin, which is a 2-part series, and the next part will be on 18th of June. The second part that you can check. And all of these webinars, as Mustafa mentioned, are recorded and available in the YouTube channel of MIA that you can check afterwards. We are the main body supporting the 2, let's say, important modeling conference series in the water domain, being the WRR mod, so Water Resource Recovery Modeling Seminar, and the WaterMatics, so Symposium on Modeling and Integrated Assessments. You can see on the screen the next upcoming conferences. So we are organizing next year by the people in Barcelona, the next WRR mode, and in 2027 we will go to south of France for the next WaterMatics. So that's it, a very brief introduction. As I said, you can check the website of the MIA. On LinkedIn also, we are quite active. So all the communications, activities, announcements will be communicated through the LinkedIn channel as well. And also IWA Connect Plus. So thanks everyone for joining this webinar, and hopefully the next one, which is a follow-up on this one. And I hope you enjoy the webinar. So I will give the floor to Bruce, who will introduce the webinar and the speakers, and have a nice and enjoyable 1-hour session coming up.
Thank you, Saba. So welcome everyone to this webinar by MIA. This is the first of a two-webinar series on digital twins in municipal industries. This first one is going to be presentations by 3 different utilities talking about how and why they're using digital twins at their utility to support folks in there. So there will be 3 presentations. Each is going to be 10 minutes. Please, can you submit your chat questions at the Q&A function at the bottom of the screen in there, and we will answer them and have a discussion at the end of the 3 presentations. I think I've mentioned each one is going to be 10. All the attendees are going to be muted and off video, so please know that. And I think that's it for the intro of the generalities there. I'm really looking forward to this discussion and hearing from their utilities from across the world here. So with that, our first speaker is going to be Jeff Sparks. Jeff is a licensed professional engineer with 17 years of experience in design, operations, and process control and utility management. He holds a bachelor's degree from Virginia Military Institute, a master's degree from Virginia Tech, and a PhD from the University of Laval. He is currently the director of digital water at HRSD in Virginia, in the US of A. And Jeff leads the efforts to digitize operations, including deploying digital twins, integrating AI, and optimizing processes. Jeff, with that, if you could go ahead and share your screen. And
thanks, Bruce. Yeah, let me share, and then you let me know, Bruce, if you can see everything okay.
Yes, absolutely. Yep.
How is it? How's it looking?
I can see you so far. Yep, there you go.
Okay. Good. Hello, everyone. My name is Jeff Sparks, and today I'm going to be discussing with you the HRSD Nansemond Treatment Plant Digital Twin. So I work for HRSD, and if you haven't heard of HRSD, that stands for Hampton Roads Sanitation District, and we are a regional utility located in Eastern Virginia. And as you can see from the map here, we have pretty much the whole eastern side of the state. Everything except for the northern neck. That's that little gray peninsula up near the top of the map there. We have everything else. We have the middle peninsula, the peninsula, the south side, the eastern shore. And we have 8 major treatment plants, and they're concentrated to the southeast there. And then we have some smaller plants too that are concentrated to the north and to the east on the middle peninsula and the eastern shore. We were established in 1940. We serve 20 counties and cities covering nearly 5,000 square miles and including 1.9 million people. And like I said, we have all of these treatment plants with a total combined treatment capacity of 225 million gallons per day, or MGD. The plant we're going to be focusing on today is the Nansemond treatment plant, and that's where you see that yellow star there on the map. So the Nansemond treatment plant it's a 30 MGD plant today. It has a 5-stage BARDinfo for its biological process. And on the back end of this plant, we take 1 MGD of secondary clarifier effluent, and we run it through an indirect potable reuse facility. Now, that IPR facility right now is just a demonstration facility. And we take the effluent from that demonstration facility and we recharge the aquifer with it. And we call this process the SWIFT process, so the Sustainable Water Initiative for Tomorrow. Now, Nansemond treatment plant is currently under expansion, and after expansion, it's going to be a 50 MGD plant because we're shutting another plant down and rerouting its flow here. It's still going to have a 5-stage BARDinfo, but we're converting the second stage anoxic zones to have mainstream partial denitrification anammox, or pDNA. And then that IPR facility that I was talking about, it's going to go from a demonstration facility to a full-scale facility, and ideally, it's going to recharge the aquifer with 100% of the average daily dry flow. So as you can see, Nansemond treatment plant is going to be a pretty complicated plant. It's going to have pDNA in the biological process. It's going to have this full-scale indirect potable reuse facility. And that IPR facility has an instantaneous total inorganic nitrogen limit of 5 milligrams per liter. And if we exceed that 5 milligrams per liter at any time, we have to suspend recharge of the aquifer. And so this is a little bit about what the objectives of our digital twin, what the objectives are for Nansemond treatment plant, and that was to improve nitrification control. So more specifically, we're talking about the digital twin serving as a soft sensor for improved control and also to help us with instrument fault detection. We also use the digital twin to perform scenario analyses. So we try a bunch of different waste rates in our model, and we try to choose the best one that's going to maximize nitrification control authority. Now, while the digital twin is currently really focused on nitrification, we realize there are a lot of future opportunities for this digital twin that we haven't quite leveraged yet. And some of those include, it could serve as a training tool for the operators and also inform capital improvement project design. So if you look at the architecture of our digital twin here on the right-hand side of this screen, what you'll see is we start with the biological process IO, or input outputs, here in the bottom left-hand corner. And then these are basically our instruments that are out in the field generating signals that get transmitted to distributed control units, or what we call drops. And those are local. And then the signals get transmitted over to some control network servers. And then we have certain variables that are really specific to or important to nitrification, right? Ones that we need the model to ingest if this digital twin is going to be used for nitrification control. And of course, those variables include ammonia concentrations, flow rates, dissolved oxygen concentrations, temperatures, right? So all of these variables, these are inputs that flow from the distributed control system over to what we're calling this advanced control server for the digital twin here in the bottom right-hand corner. Now, the digital twin exists or sits within Sumo, the Sumo software by Dynamita. So that's one software package we have running on this advanced control server. The other one is CCI Cake. And CCI Cake is what we use for our data-driven models, running those data-driven models and executing Python scripts. So we have Sumo for the mechanistic model, and we have CCI Cake for the data-driven models. So another thing to keep in mind here is that we don't have data just flowing one way. So of course, data comes into and gets ingested by the digital twin or the model, but the model itself is also producing outputs. So remember, it's serving as a soft sensor, and those outputs get transmitted back to the distributed control system. So you can see the outputs from the digital twin there in the control system graphics. And some of those outputs include the maximum specific growth rate for nitrifiers, nitrifier concentration, and the mechanistic model error. Just some other things too that are of interest. The model simulation step time here for our digital twin is 1 minute. And of course, our objective for our digital twin is to have the most representative model that we can. So we've had a lot of challenges over the years with this digital twin, and some of them are kind of silly, I have to admit. So, one big challenge was power interruptions. So if you work at or help run, a major water reclamation facility, you understand that you get these power interruptions from time to time. Well, whenever we would get one, the digital twin would stop working. We were thinking, well, why is that the case? This advanced control server is connected to an uninterrupted power supply, a UPS. This shouldn't happen. Well, it turns out this UPS didn't have any batteries in it. Like I said, kind of a silly thing, but something that we realized along the way that we needed to fix. Another thing that wasn't really a problem, that was more of an inconvenience, was because this digital twin doesn't sit within the cloud, it sits behind a firewall and it's on-prem. The vendors had no real way of seeing. So when I talk about the vendors, Dynamita and CCI, they had no real way of seeing what was happening with our digital twin. So anytime we interacted with them, we had to set up a separate computer with a webcam and point the webcam at the digital twin workstation screen. We have to use flash drives to download files and then transfer those over to the computer and send to them. Like I said, not really a problem, but an inconvenience and something to be mindful of as you go through your digital twin deployment. How are you going to deal with cybersecurity? Are you going to have it run behind the firewall on-prem, or are you going to have it operate in the cloud? And if you have it operate in the cloud, of course, there are risks then with sending the outputs from your digital twin back into your control system, where we don't have those risks because of our architecture. So a number of other challenges here. Some of them include, it took us almost a year to establish connectivity between the distributed control system and Sumo, and that was due to some security certificate issues that we had to work through. And I think a lot of these issues that you're going to see here were really on HRSD. I don't mean to blame the vendors for any of these things. So even after we got connectivity between the DCS and the digital twin after that year period, we still had brief interruptions in OPC connectivity, or open platform communications connectivity. And so even when we had a brief one, the digital twin would crash. So our friends at Dynamita then developed what we call a wrapper, hence Snoop Dogg in the bottom right-hand corner of this screen here, that anytime there was a crash of Sumo, it would automatically reopen and pick back up from where it took off. So that was good. That was really a game changer for us, because we went from only running our digital twin for a matter of maybe a day or two to then months on end without interruption. Another thing we noticed is that CCI Cake had some memory leakage in that software program. So that over time, the memory consumption on the advanced control server would slowly increase until it would completely max out, and then all software would crash. So I had to program some automatic stopping and restarting of services to clear up the memory. So that was the solution there. Of course, we also deal with what I call dirty data. We have these spikes and signals that go either above or below predefined bounds. We get fixed value faults, and then we get these changes in significant changes in instrument noise, as you can see here in the bottom chart. And so we had to develop this data cleaning framework to feed our digital twin to keep it representative. And that includes identifying what we call short duration faults. So we compare the signal to a double exponential smoothing forecast. This is kind of like the work from Janelsi Alvarez, if you're familiar with that work. And if the raw signal is much different from that univariate time series forecast, we just gap fill with the forecast. And then we also have this long duration fault identification here too, which is quite a bit more complicated and requires a more sophisticated model. It's a multivariate data-driven model there. So, my recommendations for you, if you're beginning your digital twin journey, is give yourself a robust architecture, try to eliminate all single points of failure. Of course, plan for plenty of compute so you don't run into some of these memory issues. Think about cybersecurity, and really clean your data with the simplest methods possible. But just understand that as you try to gap fill these longer duration faults, those methods are going to get a lot more complex. So I need to, of course, mention my advisors that help with this process. So Dr. Charles Bott, who is the CTO here at HRSD, and Dr. Peter Van Rolhem of University of Laval. So thank you.
Thank you, Jeff. And I'll just remind everyone, please submit your questions in the Q&A functionality of the Zoom webinar here. Our next speaker is going to be Noemi Almaraz. She's a wastewater process engineer with the Technology and Innovation Department at Metro, located in Denver, Colorado. In her role, she works primarily in advanced automation projects at the Robert W. Height facility in the Northern Treatment Plant as technical and project manager of aeration control evaluations and digital twin development and implementation for process and cost optimization. Noemi has a master's degree with a focus in wastewater engineering from the Colorado School of Mines. Prior to joining Metro, she worked as an instrument and controls engineer at a consulting engineering firm with a focus on design and commissioning of water resource recovery facilities. So Noemi, if you'd go ahead and share your screen, I'll let you take it away here. Thank you.
Thanks, Bruce. Can you see my my slide deck?
I can. Thank you.
Okay, perfect. Yep. Thank you for the introduction, and thank you everybody for joining today. So today I'm going to be presenting about Metro's digital twin at the Northern Treatment Plant. So Metro has two facilities, the Robert Height facility located in Denver, Colorado. That one's 220 MGD treatment plant, and it also operates the Northern Treatment Plant located in Brighton, Colorado. That was designed for 28.8 MGD flows. That facility was commissioned in 2016 as a state-of-the-art facility. When it was first commissioned, it operated with around 4 MGD of flows. And over the last 9 to 10 years, it has seen an increase in flow. So right now we're seeing around 9 MGD of flows to that facility. So some of the main drivers for implementing a digital twin at NTP has been, as I mentioned, the increasing loads and regulatory pressures. So with the new loads that we're adding for that facility, we have new connectors, and some of those connectors have industrial and municipal dischargers. So those industrial discharges have added more nutrient loads that the plant was designed for. So we're seeing some challenges with treating ammonia or nitrogen and phosphorus, um, which has been kind of a big challenge for operations in terms of trying to maintain regulatory compliance as well as trying to reduce energy and chemical usage at the facility. The facility is also preparing for a new permit in the near future. So we're kind of getting ahead of the game in trying to treat to ultra low effluent nitrogen and phosphorus limits. So the digital twin is going to provide a tool for preparing, training operations, and also for optimizing our process for that future lower limits. The facility was also designed as a 5-stage bar info with multiple carbon and gravity thickener supernatant feed points. So the facility has a lot of flexibility on treatment with step feed options. So you can change your step feed ratios to try to optimize treatment and try to reduce your energy and chemical costs. We're also experiencing some operational challenges with staffing and retention. So I'm sure it's a common issue in the industry, but we have a lot of turnover in staff. So trying to train new operators has been a challenge, and providing a tool for that has been kind of one of the key components of the digital twin. We've also experienced secondary treatment issues with aeration, carbon dosing, and solid distribution. So we're trying to aim at optimizing the process to try to kind of optimize some of those components where the facility has had some issues in the past. So some of the benefits that we try to leverage with the implementation of a digital twin is Metro has a huge amount of data. We are very data rich. We have sensors. We have a lot of sensors at that facility, and we collect a lot of lab data too. So we embarked on a digital twin project at the end of 2024 or 2023, sorry, in efforts to try to leverage that data and try to provide training and operational readiness tools for operators so that they can do some training in a risk-free virtual environment, and they can do simulations for shifts in flows and loads in operation. There's also a kind of a big benefit in enhancing process monitoring as well as providing process optimization tools for early detection of process upsets and running scenarios for adjustment of different set points and process changes. And ultimately, this is aimed to optimizing resource uses and then also reducing costs in chemical usage and air usage. So what makes a digital twin functional? So some of the data requirements and limitations that we kind of work through. So you can see here on the right-hand side, kind of a very general overview of the architecture from the facility. So we have the plant process data, so sensor, pump flows, flow meters. So all the data is fed into our SCADA system, which is located in the process network. The way that we initially implemented the digital twin, we had the vendor integration platform, which we're working with DHI, located in the process network, but we shifted gears towards having everything for the digital twin in the enterprise network, and then having data being pushed to the cloud to be used on the digital twin user interface. So you can see here in this data map, we have a PyHistorian. So most of our data from SCADA is fed into a PyHistorian, and then we also have the lab management system, which we use to feed data into the vendor integration platform, and then that data is pushed to the cloud and then used in the model and the digital twin interface. So we do daily lab data pushes for 24-hour composite and graph samples. And then we also do process and sensor data pushes from our PyHistorian. And then again, as Jeff mentioned, data quality is a very important. So tracking erroneous data as flatlands and outliers was a key component of kind of our data integration plan for the digital twin. Some things to consider, as I mentioned, Metro is beta data rich. We have so much data, so we didn't run into this problem, but you may run into a problem with low lab data, sampling frequency, not capturing dynamic changes for your model. And then also if you have limited sensor coverage in key process areas, that can impact the model predictions and accuracy. And also sensors and lab data don't often reflect the changes in infrastructure. So if you move a sensor, that's a kind of a manual change that has to be performed in order for the model to know that that sensor was moved from one location to the other one. And then just overall cybersecurity concerns and cybersecurity considerations need to be taken into account when you do your data integration. So just making sure that your data flows and your data maps make sense for security purposes and for just the utility of the digital twin. So yeah, data quality, very important, and data flows are also very important. So for our digital twin, we are in the final stage of implementing the digital twin for use. We're aiming at having process engineers and data engineers using it for running simulations and kind of running different scenarios for implementing different technologies and different operational scenarios that we can recommend for improving process performance. Operators can use it as a tool for informing of how the process will be affected with set point changes, and also as a training tool for new operators who might want to understand how the process reacts to different changes in the facility. And then also operations supervisors and managers can use this tool for optimization, reducing costs, and just getting an idea of the performance of the facility under different conditions. So some of the kind of initial optimization focus areas that we kind of targeted as part of our digital twin was the solids management. So trying to reach ideal MLSs and clarifier performance so that we have a stable effluent nitrogen and phosphorus and simplify operations. As I mentioned before, we also have different locations for dosing carbon in our secondary process. So trying to deal with the carbon management and optimize that to lower chemical use and have stable biological performance. Also, the mixed liquor return management to reduce pumping energy and improve treatment reliability, and step feed so that we can try to find the optimized ratio for stable effluent nutrient going into the river, and then reduce filamentous growth. And then we also want to kind of use this digital twin for trying to optimize our aeration strategy. So I think that kind of is coupled with some of the other focus areas like solid management, trying to maintain stable and reliable effluent nitrogen and phosphorus effluent limits. For building trust and driving adoption of digital twins, so building a strong technical foundation is key. So for our digital twin, we use a WEST model, but the facility did have a BioWin model, so we used that BioWin model that the plan already had to kind of build the digital twin model that was required. So we didn't have to start from zero. We had a kind of a foundation to go off of. We also started with a pilot. So we're doing a pilot of the secondary process. So the digital twin is focused on just the liquid stream secondary process. And we want to do that pilot first and then show the value of that initial iteration, and then based on feedback, kind of expand from there where other process areas that might be or provide meaningful optimization for the facility. And also strategic resourcing, so using the vendor, consultants, and defining clear roles and responsibilities for every team member involved is key for ensuring that the project kind of progresses and the technical components are kind of addressed in a timely manner. And the data quality is also very important. You want to make sure that the data you feed into your digital twin is reliable so that your outputs are reliable as well. For the adoption side of the project, we actually implemented change management strategies. So the ADCAR strategies by PROSI to identify barriers in awareness, knowledge, ability, and reinforcement. So we try to identify those early in the project in efforts to try to address any potential barriers early on and make sure that all stakeholders were on the same page moving forward with the project. The project, we also assigned champions, so cross-functional leads from different departments so that everybody was informed and everybody had a say in the development of the digital twin. And again, as I mentioned before, we engaged all stakeholders early and we engaged them often to make sure that that they were involved in shaping the adoption and development of the digital twin. So key lessons learned from our digital twin journey, defining clear goals and real use cases with measurable outcomes was very important so that people see real value and benefits into implementing these technologies. Stakeholder buy-in is critical. So just making sure that staff is engaged early and often that helps build trust. And then having quality data so that ensures that the inputs to the model are reliable and the outputs to the model are reliable. And then kind of starting small, so doing a small pilot to prove the value and then expanding from there just based on the outcomes of that pilot. And with that, I just want to thank everybody, send a big thank you to everybody at Metro who helped with this project. And yeah, thank you for your time.
Thank you, Nohemi. Nohemi, sorry. And again, remind everyone, please submit your questions in the Q&A. And now I'd like to introduce our next speaker, Ruud Peters with Waterchamp Dommel. He's got a bachelor's degree in general operations technology, a master's degree in integral design. He started his career as a process automation company at a process automation company, moved on to roles focused in system design and innovation management in various other organizations. He's now been with the Dommel for 15 years in the Netherlands, including 7 years fully seconded into the national platform for promoting energy and resource recovery. Currently, he works as a senior policy and innovation advisor. And in this role, he leads the digital twin program at the Dommel, which was initiated as part of their data-driven working strategy. Ruud, if you would share your screen and we'll make sure that it works okay. Okay, yeah, I see it. You're muted though. There you
go. Thanks, Bruce, for the introduction. Thanks for the invitation. Okay, my screen is shared. So this digital twin is going about the Eindhoven plant. It's the largest plant that we as Waterboard Dommel have. It is about 750,000 people equivalent. Yeah. So a bit of a historical background. We are using modeling for almost 2 decades now. We normally use it just for design optimizations. So there was of course, no dynamic modeling involved. I think in 2010, 2015, manager of operations asked us the Department of Innovation at the Dommel to build a simulator, wastewater treatment simulator, to train operators and to make them better at their job, and also because of people are moving into other jobs, etc. So we see that normally the older staff knows about all the exceptions, etc., and the younger staff doesn't. So it would be a great tool. Then we gathered all the scattered ideas and made a roadmap for a digital twin. First, to make a simulator, and then we saw all kinds of possibilities that we could also include in a roadmap to make an engaging roadmap, which we led our whole endeavor into the digital twin world. Then we already had a partner, Biomath from Uganda, which we already did modeling with, and later we partnered up with DHI that were already having a digital twin, which we are all now developing further and further. Yeah, so the goals that we identified was first, of course, the operator training. Then we see optimal setting support so that we can play around with the scenarios that we can choose the best settings for PID controllers or all kinds of different decisions. Although the other thing is that we have plans where we have, of course, multi criteria. We have effluent quality, of course, but also plans where we make biogas, and also we claim CO2. And another criteria is, of course, low electric bill, as you can say. So all of these criteria can we hope to get these into the model, and that it can advise us and maybe later on close the loop and ingest set points in the SCADA system. But that's not the way. That's not where we are now. Decision support for plant maintenance and projects. That was a big thing from another process of the DOML. Nowadays, when somebody wants to do maintenance on a big tank from the wastewater treatment plant, what is the impact of it? With this simulator, we can now easily simulate it and see if there are some measures needs to be in place or not. Design decision support is something we're doing already for years, and now we can do it a lot easier with not an extra vendors or advisors. We can do it by ourselves. Calamity training, that was a good idea, but we're not seeing that in the near future. Maintenance of sensors is something we will try doing in the near future. And the biggest thing that we saw that operators are interested in is the failure and response analysis. So they, of course, get messages during the night when a pump fails or some other equipment fails, and they can then put that in the digital twin, make the capacity of the pumping station, the air compressors or whatever, to a different capacity, and then the digital twin can just process that, and then they can see if they need to get out of the beds or not. Goals of the project, this all should lead to that we learn better process understanding by using the model, so we gain a deeper knowledge. We already see that when we engage with the operators, there are some questions that they never ask themselves come up, and they really need to ponder on why is this happening. It's already a big knowledge step. Of course, then there comes the limitations of the model. There are always limitations, and they got that really fast. And then learn to optimize set points and verify in practice. Learn to deal with multi-criteria optimizations and assessment using understandable dashboards. So that's the next step. and ultimately be in control over an adaptive and complex system and its requirements. So these are our goals. The intended end users are the operator and of course also the process engineers. They collaborate, and the operators are doing everything on a day-to-day basis of the plant, and the process engineers are more like for the strategy for weekly or or the design, depending on the requirements that we saw for this whole endeavor is a clear vision, outlook, and inspiring roadmap. We struggled with this idea about making a digital twin for quite some time, and we think it lacked this. And afterwards, we saw a movement coming. Management engagement, of course. Yeah, we had a management question from the operator management, so that was good. And support and budget. Yeah, we do this under the umbrella of data-driven operational excellence. And this is our we have a budget for this in our innovation process, so that's where we fund this from. Yeah, we need different roles for this project. Of course, project management, transforming needs into goals, vision on the application, so not just doing what is transforming needs into goals and vision. So, and we need, of course, substantive sparring partners for partners like modelers, graphic interface builders, data scientists, ICT, and process automation environment people. Of course, we need good partners for modeling and the user application. And technical stuff like the model, data pipeline, architecture, etc. Something about the costs. We see that in the development phase, we have a cost about 100K per year. And we think that it is like 3 to 4 years, our estimate, that will be in the development phase. And we hope that the operational phase will be something like 50K euros per year. In-house, we spend like 500 hours per year, and in operational phase, I think we will do with 200 to 400 hours per year. These are rough estimates, not yet clarified, but just rough estimates. Yeah, we have quite a complicated plant. Also, this of course reflects in the modeling. We had we made a convertimization modeling, just so not just tanks and series anymore, because we had some biokinetics in that are where you can't use tanks and series. We do everything in the West model, and we're working on automatic calibration, but that's a study that UGent is working on. The architecture, yeah, it's the same as the previous speaker. It's also from DHI, where it's our vendor for now. So of course we have our live plans. We work with an iHistorian from GE. That's a local instance running on every plant, and it is synchronized on our headquarters. And at headquarters, there's a gap filling, etc., and data cleanup, and then it goes to the Azure cloud, where also the web interface works. So this is more the data cleaning part. It uses rainfall and influent prediction to fill the gaps, and it also labels all the data that it ingests into the cloud. So how does it look like? This is a plant status picture. In red, we have here the predicted value. This is the influent, so it uses an influent predictor. And the yellow one is the measured. Okay, this is the time of future, so everything before here, it's simulated is the same as the measured. And afterwards, we can see the quality of the prediction. So here it missed it, so we need to do some work on the influence generator. Next slide. Yeah, the main part of the application now is the learning plan. We see here, this is where everything can be changed. You can change time series and other parameters. Every handle you can think about that's in the model we can expose. And yeah, so for instance, we can of course, for maintenance, we can add or not, we can remove a tank and then see what it goes, or we can change the pump capacity, but we can also change the, yeah, everything you can think about. Yeah, the performance in use up till now, the customer, so our manager of operations is on board, totally on board. The operators see the benefits of the digital twin, but we're also struggling with operator and process engineer engagement. Yeah, operators need to get more accustomed to it, and we try to do that via workshops. But we also need process engineers that really dig into it, and that also take ownership of the digital plant, just as that we have ownerships roles for the physical plant. And yeah, of course you have staff that is yeah, some are not really into the digital world and others are, but yeah, it's a bit of a, yeah, it's a hurdle to come. Also, the system is not yet reliable enough, as we see, and fast enough to be used in day-to-day operations for operators. For process engineers, a different story. But I think this will be overcome. Another picture. It's not. I think it's the same. Yeah, as a summary. I think this is more for reference, so we can leave it here. So you can read this, and we have the slides later. So thank you.
Thank you very much, Ruud, and other speakers there. So now I would like to ask the Noemi and Jeff to turn on their cameras, and we will get into the discussion period here. There is one question in the Q&A for Jeff, actually. Jeff, could you please explain how the influent generator of your digital twin at the Nansemond plant is designed?
So there's actually no influent generator. We're not making any kind of flow rate or concentration forecasts, right? Like we use all of the raw signal and sensor information from our field instruments to then feed the model. So we're not generating any signals. We're not forecasting anything.
Great, thank you, Jeff. Let's ask. I'm going to let each of you answer this question. So you talked about how each of your utilities is currently using and developing these digital twins. But what do you see as the next steps in each of your utilities? If you had the best next step to happen, what would that be in your plant right now for the use of the digital twin or the advancement in some way? You know, Jeff, you're big on my screen right now, so I'm going to let you answer first.
Sure. So, you know, the thing that we're working on right now, and I mentioned this in the presentation, is trying to use the digital twin as a soft sensor for instrument fault detection. So we've been real big on using it for nitrification control. That's why we soft sense the maximum specific growth rate for nitrifiers. It's why we soft sense the nitrifier concentration and the mechanistic model error, because all of those things roll up to this formula or this equation that generates a DO set point for us to do the best we can with nitrification control. So that's really been the focus. But now we're shifting, because that part of the project is pretty done, to using all of the data we're getting back from the digital twin to help us with instrument fault detection. So we should be able to compare raw sensor signal data to digital twin soft sense data and come up with what are some typical deviations. And then when we see big deviations that don't look like the typical or look like the norm, we should be able to generate an alarm and then troubleshoot that. So that's really the big next step for us. Yeah.
Fascinating. Great. So you're going to be using a digital twin to help maintain your instruments in there.
Yeah, absolutely. Yep.
Yeah, cool. Noemi, what's your answer?
Yeah, so for us, we want to build confidence in the model and the predictions of the model so that we can create recommendations for set point adjustments to the process so that we can optimize the process. We are hoping that operators get comfortable with the recommendations and start using those a little bit more. Once we prove the value and the reliability of that, we're hoping to expand. I think I mentioned that we're doing a pilot of the secondary process. We want to expand and do, the solids process as well. And then do more of the energy side of things as well. So try to capture that. So it'll be kind of like step by step, trying to prove or scale little by little, just make sure that we are cognizant of the learning curve and the amount of information we provide operators and the end users.
Okay, so you're kind of in the trust building phase around this right now. It's kind of what
Yes.
you're in there. Okay.
Yep.
Interesting. Thank you. Ruud, your turn. What's your next steps?
Yeah, a bit also like Noemi said, trust building is also one of them. For sure, more engagement of operators and process engineers on a more daily or weekly basis is our goal. And after that, or maybe another goal is to include also the sewage catchment and also the surface water, so that we have an integrated model for for the whole thing. And we have the models, so it's just not just a matter, but it's a matter of putting them into the digital twin environment and see what's going on then. So yeah, those two.
Very good. Thank you in there. Okay, we had another question show up in the chat. And this is a good one. And Jeff, I'm going to let you take a first shot at this one here. In what ways is the digital twin different from a SCADA system? And what value does it add to complement our current SCADA system with a digital twin?
Yeah, so as I mentioned, for us, we're primarily using it as a soft sensor and for scenario analysis. So, a SCADA system or traditional instruments, I think you could come up with a way to build an analyzer that would tell you what the maximum specific growth rate for nitrifiers is, right? In fact, we've toyed around with this idea and we started even development of one, but it's hard and it's complicated. And I don't think there's one out there on the market that can do it for you. And so, yeah, I think the digital twin just does things that are just quite frankly impossible with traditional methods. So that's one big difference. Like, it's just hard to get some of this information any other way. So that's one thing. But the other thing we're doing are these scenario analyses to tell us what the ideal waste rate is for what we think are going to be conditions that are coming soon, right? Like big shifts in temperature, right? And these are really important because we have these instantaneous nitrogen limits that we have to comply with, and so the waste rate's got to be just right, or else we're also wasting a bunch of energy and chemical. So again, this is really hard to do with a SCADA system that doesn't have a model. So yeah, I think these are the big differences.
One question or comment for you in there. You've implemented your digital twin on-prem, and in the past you've said things that the digital twin itself is not actually very visible. You've implemented it as just essentially another control loop within your SCADA system there. Could you talk just a little bit to that?
Yeah. I mean, it's primarily a tool right now for process engineers who are going to interface directly with the digital twin. But that being said, there's information that comes from the digital twin and can be displayed in the DCS, or if you want to call it SCADA system graphics. So that information from the DT is available for viewing, but for interfacing directly with the Sumo model, that's typically something that's just done by the process engineers.
Noemi or Ruud, do you want to add anything to that?
Yeah, the obvious difference is, of course, that one is model-based and the other is just simple control loop-based. So there are a bunch of different controls that are interacting or not interacting, if you make a feed forward or not. And then the model is, gets the whole thing. So that's the big difference. And then in terms of what you can do with it is of course then also easy to show. So you can make predictions and all that stuff, which you can do with a SCADA system.
Excellent. Noemi?
Yeah, I think like the use of predictive models, machine learning models, is something that you won't be able to do in SCADA. So having a interface outside of your SCADA or like Python or some other platform, adds that value of allowing you to do like an influence generator or predicting different parameters in your process or your model.
Excellent. Thank you. Well, my clock says we're at the top of the hour in whatever time zone you're in, unless you're in one of those odd half-hour time zones in the world. Anyway, I'd like to thank our speakers for presenting on their use of the digital twins, and would ask that everyone, if you can, please participate in the next part of this webinar. Again, thank you, speakers, and I hope everyone has a good rest of your day wherever in the world you are. Thank you.
Thank you all.
Thank you.
Thanks.